The pictures of Mars returned by spacecraft show it to be a fascinating and diverse planet with massive volcanoes, deep canyons, and dry riverbeds. Only 2 sites on the surface have been explored in detail, but since they were chosen for their flatness and lack of features, these sites are located far from the most interesting geological areas. The next step in the exploration of Mars is being planned now, going over this horizon. But the terrain is rough, especially for a robot rover controlled from the Earth. The rover could simply transmit pictures and wait up to 40 minutes for new instructions from the Earth. Or it might possess adequate artificial intelligence to find a safe path through this obstacle course. The Mars Ball group chose a third approach, which is to make the rover large enough and rugged enough that the rocks and boulders become small in comparison. Jacques Blamont of the French Space Agency suggested a practical way to build a large rover. Make its wheels inflatable and propel it by altering the shape of the wheels. This artist's conception shows one possible implementation of that idea, a large 2-wheeled single-axle vehicle. This rover would roam the Martian surface without sophisticated onboard intelligence and without continuous instructions from the Earth. A group of graduate students at the Lunar and Planetary Laboratory of the University of Arizona set out to construct and test a prototype vehicle using this novel method of locomotion. Using only low-cost, low-technology materials, they built a rover known as the Mars Ball to determine if such a design would work and to study its capabilities. During the flight to Mars, the rover's wheels would be deflated. On arrival, the wheels would be inflated using the local Martian atmosphere. When fully inflated, this test vehicle stands about 4 meters high and 5 meters wide, dwarfing the half-meter-sized rocks seen at the Viking lander sites. Even though this rover weighs 500 kilograms, it is supported by a pressure of only 50 millibars. A similar rover in the lower Martian gravity would require only 15 millibars of pressure. The Mars Ball does not use motors to drive its axle. Instead, it rolls by sequentially inflating and deflating the sectors in contact with the ground. As the sector on the right inflates, the tire moves to the left. The sector to the left now moves into position to deflate, which rolls the tire further forward. This process is repeated independently for each wheel, moving the vehicle forward at a speed of about 1 meter per minute. While this sounds very slow, it would allow the test rover to travel 1 kilometer per day. The vehicle has no front or back, so the inflation sequence can simply be reversed to travel in the opposite direction. The sectors are inflated and deflated through valves connected to electric blowers located inside each hub. When a sector deflates, its air is vented directly to the atmosphere. An actual Mars version would recycle the compressed gas between sectors to save energy. Each valve is controlled by the onboard computers. The motions of this test vehicle are directed by a human operator. In addition, simple programs have been developed which allow the rover to roll indefinitely on level terrain without human direction. Similar programs for climbing slopes and obstacles are possible. The Mars Ball design does not require sophisticated onboard intelligence or frequent contacts with Earth to traverse terrain with moderate slopes and obstacles. The vehicle goes over rocks and other small obstacles more by absorbing them than by climbing over them. The number of deflated sectors would be adjusted by internal computer control to roll over rocks of various sizes. The Mars Ball climbs slopes by changing the simple inflation-deflation sequence. An earlier prototype of slightly different design climbs slopes of up to 24 degrees. The two-wheel single axle design allows the vehicle to turn by rotating in place. The central black structure would house soil and rock samplers, TV cameras, and other scientific instruments. This payload section always hangs below the axle and can be lowered to the ground for scientific experiments by deflating the tires. This prototype has confirmed the theory behind the Mars ball concept, but a number of practical problems must be addressed in adapting this design to Martian conditions. The bag material must be puncture-proof and flexible at low temperatures found on Mars. The compressors and valves must work efficiently in the thin Martian atmosphere. Increasing the number of sectors per wheel should increase the slope and obstacle climbing abilities of the rover. The Mars ball will also require simple sensors to detect slopes and large obstacles. The unique design of the Mars ball offers several advantages. It's inflatable. This allows a large rover to be flown to Mars in a small package. The Mars ball is simple and inexpensive to operate. The large size of the vehicle allows it to ignore most surface obstacles. This removes the need for constant communication with mission control or sophisticated onboard computers. The group has calculated that the Mars ball could operate on solar cells. The Mars ball is inherently stable. Its width greatly reduces the likelihood that the vehicle can be overturned. Exploring Mars will be a difficult but exciting project, calling for new ideas and innovative designs. The Mars ball is one possible solution to this challenge. To obtain a technical description, a copy of this videotape, or other information, please contact the Mars Ball Project.